Hey, this is a video for our next topic, which is A3. And, in A3, we're going to cover a whole bunch of derivative rules. Okay, so let's just talk about A2 for a minute. So what we started with was figuring out that, well, actually, let's even back it up to A1. So what we started with was looking at different functions and how to find a rate of change on the function. So, the first thing we started with was, we're like, how would we find the slope or the rate of change? Oh, we could pick 2 points and figure out like rise over run, right? That's how we started. And then we were like, oh, we really want to narrow it in. Like, we want to find the slope at just 1 point. So we would take this point and back it up, make it like really close to the other point and find the more accurate slope. And then we got into the topic of limits, where we thought, well, if we could make this interval, which we called h, really, really small, we could approximate the rate of change just at 1 point. And we called that, like, we were finding the slope of a tangent line to the curve at 1 point. And now we're calling that a derivative. So derivatives are just the slope of a function at 1 point. So if we wanted to find the derivative of f of x, so let's say this is a graph of y equals f of x, the way that we learned in A2 was that we would do something called first principles. So we would define the derivative, which the notation could be f prime of x, or it could be the Leibniz notation. Whoops. I'm so sorry, guys. That should be an x on the bottom. So the derivative of f of x with respect to x. So those are the different notations we used. So this is first principles definition. So we found the limit as h goes to 0, meaning, we want to find the slope right at that 1 point. So we want that interval to be nothing, of f of x plus h minus f of x over h. So that's what we call first principles. So that's what we kind of focused on in A2. And it's a lot of work. Like, if you wanted to find the derivative of like y equals 3x to the power of 4 minus 2x squared, like that's going to take you forever. Because you're going to have to write an expression for f of x plus h, and then subtract it from f of x, and then divide the whole thing by h, and simplify it, and it takes forever. So mathematicians have derived a set of rules that make finding the derivative way easier than this guy. Okay, so this is where it all comes from. So you need to understand that. Okay, but now in A3, we are going to get into all the rules for derivatives so that we no longer need to use this guy. But that one's where it all came from, so it's really important that you do understand that formula. But now that we're in A3, you can just use the derivative rules. All right, so I'm just going to teach you 2 rules in this video. And the first rule is called the constant rule. And it's just for finding the derivative of a constant. So if you had f of x equals some constant, we'll just call it c. So for example, if f of x equals 8, or f of x equals -2. So if the function is just equal to a number, then it turns out, I'm just going to give it away, the derivative of that is always equal to 0. So the derivative of a constant is always 0. And if you think about it graphically, that definitely makes sense. Because graphically, okay, let's say we wanted to graph y equals 2. Okay, so we know y equals 2 is going to be a horizontal line at y equals 2. And since we know the derivative is the slope at every point, then just think about it. The slope at every point along here is going to be 0, right? It's a horizontal line, slope of 0. So that totally makes sense. We could also prove it because, we can find the derivative using first principles. So if I wanted to whip out that formula, if I wanted to find the derivative of a constant, I would take the limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay, so we take the limit as h goes to 0. Now this part's weird because since we just have a constant, there is no x, so there's not really an x plus h. So f of x plus h is just c. And f of x is also c. Because since there's no x value, you can't really put the plus h. And it's divided by h. Okay, so this part's kind of weird, but I guess since c minus c is just 0, then you know what? Before we even sub 0 in for h, we can just say that, well, we know 0 divided by h is going to be 0. Then we just get rid of the h, and therefore the derivative is 0. Which we showed that that totally makes sense, that the derivative would be 0 because the slope is 0 at every point. Okay, perfect. So that's called the constant rule. So anytime you're given a constant, you know that the answer, the derivative, would be 0. So for example, somebody gave you the equation y equals negative 4. Find the derivative. And you say, okay, dy by dx equals 0. Boom. Okay, so constant, done. Next rule. This one's super important. I feel like you use this rule all the time, and you use it in combination with other rules, and it's called the power rule. So, for example, let's take f of x is equal to x to the power of n. Then I'm going to give it away again, and then I'll prove it. Okay, then the derivative of f of x, so this is your rule here. So if you want to keep like a set of notes, this pink part, this is the actual rule. Then the derivative is equal to n times x to the power of n minus 1. So that is the rule. So I'll just show you a quick example. So just example in case you hate letters. If you had y equals x to the power of 4, then the derivative of that would be 4x to the power of 3. That's what the n minus 1 would be. So you'd subtract 1 from your exponent, and you'd stick your exponent out front. And that is called the power rule. And let's prove it. Okay, the proof for this is a touch challenging. It's a little bit weird. Okay, but let's prove it the same way we did the other one. It's just going to be a little messy. All right, so if you have, if you want to take the derivative of anything, you can use first principles. So limit as h goes to 0 of, I'm just going to write our original, f of x plus h minus f of x divided by h. Okay, so if we have to sub in f of x plus h into here, then that would just become x plus h to the power of n minus x to the power of n, and the whole thing is divided by h. Okay, here's where it gets tricky. So you kind of have to think about the numerator here as being like something, let's call it a to the power of n minus b to the power of n. So it's almost like this part right here, x plus h, I'm just calling it a. And then x, I'm calling it b. So it's like you have two terms to the power of n, and they're being subtracted. So it's almost like you had, like, you know, difference of squares, if you had like x squared minus 4. Another way to write that would be x squared minus 2 squared. And we know it always factors into brackets, like x minus 2, x plus 2. So I'm going to use my knowledge of how difference of squares are factored. Or even like if I had this, like I'm going to use my knowledge of how to factor binomials that have a subtraction sign and could be raised to any power. So I'm actually going to factor my numerator. Like, you don't have to do this ever. I'm just proving this. Okay, so limit as h goes to 0. And what I'm going to do is I'm going to factor out, like, see how in difference of squares we factored out an x minus 2? So I'm actually going to factor out an a minus b. But a is actually x plus h. So I'm going to factor out an a, which is x plus h, minus b, which is x. Okay, so I'm factoring those out. And then in the next bracket, here I just had an x plus 2 because I only had squared. But here we're saying it's to the power of n. So here's how the factoring situation works. So you take whatever a is, so x plus h, that's what a is, and you raise it to the power of n minus 1. So for example, in the difference of squares, see how n was equal to 2 here, and see how here in the second bracket, x is now to the power of 1. So it's like 1 less than n. So that's why we do that. It's complicated though. Plus our next term would be, we're just going to follow a pattern. Our next term would be x plus h to the power of n minus 2. But this time we're going to add in the other variable, which is the b. Because if you'll notice here, this b value is now to the power of 1. So I'm going to add in the x value to the power of 1. Plus, and that pattern is going to continue until you're down to the very end, which will be x plus h will just be to the power of 1 whenever it gets there. And then we'll have x to the power of n minus 2, and finally x to the power of n minus 1. So that's just like, it's super complicated, but it's just the pattern of how you would factor binomial to the power of n. And this whole thing is divided by h. Okay, so this is what's in the second bracket is kind of insane. But we can simplify the first bracket. So if you'll notice here, we have x plus h minus x. So we could actually get rid of this bracket. It's not really doing anything. And then we notice that x minus x actually goes away. So we're just left with an h out front. It's just an h, and then everything that was in that second bracket. So guys, I'm sorry, I'm not going to write that all over again. I'm just going to show that. I'm just going to erase it. Oh, should I? I don't know. It's going to show that all we'd have left is an h here, and we have an h in the denominator. So I can actually cancel those h's out. And now I'm just left with that insane bracket. So yeah, now I'm left with x plus h to the power of n minus 1 plus x plus h to the power of n minus 2 times x plus plus x plus h times x to the n minus 2 plus x to the n minus 1. Okay, now I might as well go ahead and sub in 0 for h. So all those h's are gone, so now I just have x to the power of n minus 1 plus x to the power of n minus 2 times x plus x times x to the n minus 2 plus x to the n minus 1. So I just went in and shoved a 0 in for all these h's. And now I'm just going to go ahead and simplify using exponent laws. So I'm noticing here I've got two x's multiplied by each other and they have different exponents, but they have the same base, so I can add their exponents. So since this has an exponent 1, that actually would just become n minus 1. And same with the next one. I should put a plus there. That would become x to the n minus 1 plus x to the n minus 1. And what you're seeing is we're just having a bunch of x to the n minus 1 terms. Turns out there are n number of terms. Right? Just like in this case, when n was equal to 2, there were 2 terms in each bracket. So since we know that there are n terms, we can actually write it as n times x to the n minus 1. So there you go. We have proved the power rule, although it is quite a complicated proof. It's kind of a weird one. All right, guys. So just to show you a couple examples of the power rule, we have y is equal to x to the power of 7. So if we wanted to take the derivative, dy by dx, that would be equal to, bring the 7 in front, 7, then write the x, and then subtract 1 from the exponent, so 6. So 7x to the power of 6. Another example, say we had f of x equals x to the power of negative 3. Now this is a weird one because we wouldn't really leave negative exponents like that. We would take care of that, but for now, I'm just going to show you what that would look like. So we bring the negative 3 out front, and then we subtract 1 from negative 3. So negative 3 minus 1 would be negative 4. So that would be like that. But just FYI, you know how in grade 11 you learned, oh my god, don't leave a negative exponent. So how you could write this is negative 3 over x to the power of 4. Remember, you can always bring it a negative exponent, write it as a reciprocal. Okay, let's do one more. So if you had y equals x to the power of 5, then the derivative of that would be 5x to the power of 4. So that's how the power rule works. So that is the power rule and the constant rule. Okay, I don't know if we have time in this video, but you can actually combine those rules. Oh, you know what? I'm going to leave that to the next video.